All right, maybe I'll start while you're racing.
Yeah, Nima can start. It's a pleasure to have Nima here, who's local this year.
So it's wonderful to be here. I'd like to thank Ashwin for the invitation to talk. I think I'm understanding this talk is pure entertainment, because at least on the face of it, this subject matter doesn't have anything to do with the actual subject matter of what I'm talking about. This business doesn't seem to directly have anything to do with the subject matter of this very nice workshop. And it's actually instead a context where combinatorial and topological issues and questions aren't relevant for determining topological questions about gapped phases, but are instead relevant for determining all of dynamics for gapless phases. Okay? And the context is that of what you can call holography in flat space, broadly speaking, and the physics of scattering.
Why don't you put this in?
Oh, thank you.
Just in case you don't hear it.
So, just to set the stage a little bit, we've gotten very used to the idea that when we have quantum mechanics and gravity, the only sort of observables we're allowed to talk about don't live on the interior of space-time, they live on the boundaries of space-time. The best example is an anti-de Sitter space. And what's wonderful about anti-de Sitter space is that it's like the inside of a box. The boundary observables that you're allowed to talk about are pinging things on the boundaries of the box, and maybe if you're a bulk person or someone who knew about this geometry and you asked this question, you would think that you would answer it by following these waves going in and crashing into each other and coming back out. But the fact that the question begins and ends at infinity suggests that there may be another way of doing the computation where you never see the inside, you only ever talk about the walls. And we now know that indeed, that we can talk about a quantum field theory on the boundary that's dual to a theory of quantum gravity in the bulk. But a very big thing that lets this duality fly is that the notion of time is left unaffected. So the time that flows on the outside, on the walls of the box, is exactly the same as the notion of time that goes in the middle. Or if I say it another way, once you get into this holographic frame of mind, and you say, well, the observables you're talking about live on the boundaries. And let's say you go to the boundary and say, what does the boundary look like? The boundary is a normal place. It's a normal space-time. It's a Minkowski space. It has a normal notion of distance. It has a metric. It's a familiar place. And so once you're in this remarkable holographic mindset, it's reasonable that the kind of question you're allowed to ask there is the kind of questions we ask about normal quantum mechanical systems that just live on the boundary. But of course, in the real world, we're very far from these observables who live on the boundaries of an anti-de Sitter space. Something closer to the real world would involve answering an analog of this question for flat space. And the analog of these boundary observables in flat space are scattering amplitudes. So we throw particles in, particles go back out. I'll use crossing symmetry to draw all the arrows as incoming. Okay, and so that's the question that we're asking. The particles come in from infinity, they go back out to infinity. And once again, we'd like to ask the actual data that labels the scattering process as a bunch of unshell momenta, or I can think about these as rays going out to the boundary of Minkowski space. If I want to think geometrically, there's a lot of ways of thinking about what the boundary should be. But the analog of this question is to find some, the analog of holography in flat space would be to find some kind of question in this space whose answer are the scattering amplitudes. And now it's much less obvious what to do there. That there's no obvious notion of locality, there's no obvious notion of time on this boundary. And so you have to do something a little bit more adventurous. You have to look for different kinds of questions. They're not going to be the standard familiar questions that we're used to talking about because we don't have an ordinary notion of time, an ordinary notion of locality, or anything like that. And there's actually a very practical reason to expect that such a reformulation of the physics of scattering process should be possible, which is that even when you do the computations for scattering amplitudes in perturbation theory, and these are calculations that people need to do for practical reasons, for gluon scattering amplitudes to make predictions for ordinary particle processes at the Large Hadron Collider, or even if you imagine high-energy protons from cosmic rays smacking into the upper atmosphere. These are natural processes, they happen all the time. We know in principle how to do these calculations in perturbation theory, but in practice the answers are horrendously complicated, even for the very simplest processes. If you compute even at tree level in perturbation theory, 2 to 3, 2 to 4, there's hundreds and hundreds of pages of algebra, and yet around 30 years ago people started discovering that the final answer was astonishingly simple. These hundreds of pages would collapse to a single term. And a little over 10 years ago, people discovered it's not just very simple, but they have hidden infinite dimensional symmetries. This is ordinary gluon scattering in the real world. Okay? No fancy schmancy special model. In leading order of approximation, tree-level scattering for gluons has an infinite dimensional Yangian symmetry, which is completely obscured in the Lagrangian formalism. Okay, so these are two indications, both conceptually, from finding the analog of this beautiful picture for something getting closer to the real world, and also practically, that there should be some new way of thinking about what this physics is. But this new way is not going to be a standard duality. We're not going to put a theory with a normal name on a normal place and do some computations with it. Now, I have very little time, so I want to be very concrete in this talk. To do that, I'm just going to have to assert some things, but it'll be self-contained. So let's say we're talking about gluon scattering. Gluons have color. So we're going to, but at tree level, we can talk about a color-ordered amplitude. Okay, so the gluons have color 1 bar 1, 2 bar 2, 3 bar 3, and so and this is going to be important. There's actually natural ordering associated with these incoming lines, 1, 2 up to n. Now the naive variables that would describe the amplitude are the null momenta of these gluons. We're going to trade those variables for another set of 4 variables. I won't explain exactly how it works. It's very simple in standard correspondence. They're known as twistor variables. And so I have an amplitude that depends on the number of particles that are scattered, on the helicities of the gluons. They have spin 1, so they can have helicity plus or minus 1. And with each particle, there's a 4 vector, z1 through zn. So for each particle, there's a zai. And there's 2 identifications. So this identification actually keeps track of the helicity weight of the gluon. So really we can think of these z's as points in P3. So we'll alternately think about them as just 4-dimensional vectors or as points in P3. And there's also a transformation that the z can go to a 4x4 linear transformation on the z. So this is in GL4. And that's the point of these variables, is that GL4 is actually the action of the conformal symmetry in 4 dimensions. Okay, so these are the best variables for manifesting the obvious symmetries of the problem. Okay, and so now we have a concrete version of our question, right? The kinematic space, the space where the amplitude lives for this problem, is not some Minkowski space, is just the space of n 4-dimensional vectors. That's it.
Color.
Yeah. Sorry?
Color indices?
It's color ordered. Okay? So there's an ordering for these particles, and so this is a particular color ordering. All right, so that's our canvas. Okay? We just have the space of, so we have a kinematic space in general. So this is a kinematic space, which in this case is just the space of n 4 vectors, z1 through zn. And now you have to ask some question in this space. Okay? There's no Lagrangian, there's no action. You have to ask some question in this space whose answer is going to give you a scattering amplitude. And the scattering amplitude has to be local and unitary and satisfy all the things that we normally derive from thinking that there's an underlying local and unitary quantum field theory. So that's the motivation for the title of my talk, is that the real purpose of this whole business is to go to this kinematic space and find a new kind of mathematical question to ask there that will then spit out answers that are local and unitary as outputs. rather than what the all-desk matrix program of the 1960s was trying to do, which was to input locality and unitarity and using to compute scattering amplitude. So we have the opposite philosophy. We're trying to find a new kind of mathematical question whose answer we can interpret as giving us local and unitary scattering amplitude, so that causality, locality, unitarity are outputs and not inputs. And this just gives you an idea of the sort of challenge involved here. What the heck are you going to do? This seems like the most boring, arid space. What can you do in the space of n 4 vectors? And the answer that we've been seeing over the last 10 years or so, but really more and more in the last couple of years, and various aspects of this are related with interesting new mathematical structures in combinatorics, geometry, number theory. The sort of buzzwords are total positivity, cluster algebras, mixed state motives, and so on. And that's the subject matter of the program at the CMSA that my friends and I are running here this semester. But broadly speaking, in this kinematic space, there are first some combinatorial and purely topological properties. These become associated with things that we call positive geometries, which are further associated with, first, a certain set of differential forms that live on this space, called canonical forms, and then, so far, then there are more interesting things, actually transcendental functions, and beyond. Okay. So various parts of this connection are solid, various parts are being developed, but I want to give you a flavor for what these ideas look like by first jumping in the middle, okay? Because to see how it is that we're going to geometrize the emergence of locality and unitarity from some different starting point. And just to say quickly what it is that we're after, one good thing here is that if you just sum up tree Feynman diagrams, as I told you, there are thousands of pages of algebra, but it's possible to check whether you're right or wrong. It's possible to check whether the answer is right or wrong without doing the thousands of pages of algebra, because locality and unitarity have a very clear fingerprint in tree amplitudes, a property of these rational functions of the momenta that allow you to check if the answer is right or wrong. And the fingerprint is quite natural. If you think about what the tree amplitudes look like, you know that when some subset of the momenta go on shell, the amplitude has a pole. The amplitude has a pole there, and on that pole it factorizes. Okay? So the fact that it has a pole only when a subset of the momenta goes on shell and nowhere else, that's locality. And the fact that it factorizes on the pole, that's unitarity. So that's how you can check whether your answer is local or unitary. Someone gives you a function that has a crazy pole like p squared q squared minus r squared t squared is obviously wrong. Okay, but even if they give you a function that has a pole in the right spot, but you go on the pole and it doesn't factorize into lower things that you've seen before, it's also wrong. Okay, so the goal is to find some way of guaranteeing that this is true without drawing pictures of gluons propagating across here at tree level, which of course guarantees that it's true. And the claim is that there's a totally topological question in this kinematic space that forces that. A very simple topological question in this kinematic space that forces that. So that's the sense in which, as I said, combinatorial topological issues are going to give us locality and unitarity. But I think I have 10 minutes left. 10, 15 minutes?
Yeah, let's say 10 minutes.
All right, let's say 10
plus a little bit time.
All right, great. So let me just give you a flavor for how this works. Just to say, in terms of these z variables, these twistor variables, that the thing that I erased about factorization is actually the following statement, that if I think about these z's as points in P3, that there's a pole when the 4 points I plus 1, so if I have this amplitude like this on the factorization channel, there is an index I and an I plus 1 here, and a j plus 1. So in terms of these z's, I'm looking at a configuration. This, in terms of momentum space, translated in terms of these twistor variables, to the line I plus 1 intersecting the line jj plus 1, or otherwise saying those 4 points in P3 are coplanar. So generically 4 points are not coplanar, so I have to go to a special configuration. When the 4 points are coplanar, you notice that we give birth to a new interesting point here, intermediate, and so the amplitude is supposed to factorize into the product of the guys on the left with intermediate and the guys on the right with intermediate, just like we see in this picture with ordinary momentum. Okay, so that's what has to come out, and now I want to explain how these things are going to come out. So the first part is to actually tell you the connection between geometries and certain differential forms, because the amplitude is going to end up actually being a differential form that lives on this space. So now positive geometry in general is a generalization of triangles, polygons, polytopes into more abstract spaces, Rosmanians, toric varieties, etc., etc., etc. But in all cases, it shares the feature in common with those familiar examples that it's a space that has boundaries of all codimension. Codimension 1, codimension 2, all the way down to points. So let's say you have, so I'm going to illustrate what the notion of a canonical form associated with the geometry in the simplest possible cases, where the geometries are just essentially simplices and generalizations, polygons, polytopes. Let me just begin with a one-dimensional story. Let's say I just have one dimension, and here's the most obvious space I could talk about, the inside of some interval. Okay? So that's a space, the inside of an interval, at x equals, with boundaries at x equals a and x equals b. And I want to claim that with this interval is associated a certain canonical differential form, which has the property that it has logarithmic singularities on the boundaries of this space. And only on the boundaries of this space. Logarithmic means that locally it looks like wedges of dx over x. There are sets of coordinates where locally it looks like wedges of dxi over xi. In this case, it's just one-dimensional, so this form is dx over x minus a minus dx over x minus b. And here the only interesting thing to say is about the minus sign. Why don't I have a plus sign there? Because if I had a plus sign, this form would have logarithmic singularities at a and b, but it would also have a singularity at infinity. Okay? And I don't want it to have a singularity anywhere other than at the boundaries. So that's what determines this notion of a canonical form. It's a form that has logarithmic singularities on and only on the boundaries of the geometry. So that forces a minus sign. So next, let's say I have a triangle. So here's a two-dimensional shape, the inside of a triangle. Let's say this boundary is the line 1 minus x minus y equals 0. Here's x and y. In this case, the form, it's a two form, and it's obvious, dx dy, where xy, 1 minus x minus y. So these are all trivial, but again, you can check that if you take now the residue of this form on any one that sets you on any one of these boundaries, you go from a two form to a one form, and the one form that you get is the canonical form for a one-dimensional positive geometry. Okay? It gets more interesting when you have a quadrilateral. So let's say you have a quadrilateral. So now, so I have sort of four lines defining the boundaries of the quadrilateral. So now I might think that this form is dx dy over L1, L2, L3, L4. But this can't be the full answer. This certainly satisfies that it has singularities in codimension 1. But let's say I take a residue on one of these lines. Then you see the resulting form could in principle have singularities here, but also at this bad point, where these two sides that aren't actually in the quadrilateral intersect up there. There's another place it could have a singularity, over here. And so if I don't do anything else, this is going to be wrong. This is not going to have logarithmic singularities on all the boundaries. So what I have to do is put a numerator, which actually is the straight line that kills and goes through those 2 points. Okay, so in this case, you see already you get a slightly more interesting form when the geometry gets slightly more interesting. And in general, positive geometries are exactly these objects. They're spaces with boundaries of all possible codimension with this unique canonical differential forms tied to it. So the differential form is a slave to the geometry and is totally determined by this requirement that has logarithmic singularities on all the facets and all the way down. Okay, so let me finally say what the emerging story is that we've been seeing, and as I say, we're exploring many facets of it and other things at this program. So let's go back to the kinematic space. So where are any of these geometries in this kinematic space? Well, so in this kinematic space, in our case, just a space of 4 by n matrices, Z1 through Zn. There's first of all some part that we call the positive part. And this part is going to be totally determined by topological considerations that I will tell you about in a second. That's the only thing I'll tell you about in the 5 minutes that I have left. But there's a second part which is much simpler, so I won't talk about it. A second part is to find a family of subspaces. So if you remember, my amplitudes were labeled by n, and they also had some helicities. I don't think I defined this integer k that counts how many of the helicities are minus. That ends up being an important variable. So the amplitudes actually depend on n and k. So this is a subspace whose dimensionality is 4k dimensional. So there's a 4k dimensional subspace. The amplitude itself is a certain 4k form that's defined on the entire configuration space. It's defined everywhere. But it's totally determined by the following property. It's totally determined by the property that when you take these subspaces and intersect them with the positive part, you get a positive geometry. That positive geometry in this particular problem is called the amplituhedron. And this canonical form pulled back to the subspace, this form pulled back to the subspace is the canonical form for that positive geometry. Okay, so all of the juice is in telling you what determines P, because the choice of the subspace is basically forced on you and is canonical. So all of the juice is to tell you that in the space of 4 by n, in the space of n points in P3, in the space of n four-dimensional vectors, there is an interesting part. And that interesting part is going to be determined by this topological condition. So let me just spend 3 minutes and describe what that condition is. In fact, the 4 here doesn't matter. So we can do this for any old m. So n equals 4 if we care about normal gluon scattering, but we can do it for any m. And so let me illustrate what the idea is for even m. It's actually something a little bit more primitive and fundamental, but I don't have time to explain it. Let me explain what it is for even m. So let me first tell you, how can we pick out, in the space of just two-dimensional vectors, just two-dimensional vectors on the plane, some interesting part, okay? And the interesting part is just characterized by winding number. So I'm going to ask that these vectors, so there's some origin, there's a bunch of points. I'm first going to ask that all of these, if I think of these as two-dimensional vectors, if I look at all these determinants, zi plus 1, that all these determinants are positive. That just tells me that they're all sort of winding around in the same direction. So that's one sort of simple picture for what it could be. But in addition to that, in order to specify what this interesting configuration looks like, I have to specify the winding number. So I have to tell you how often it winds around. So I have, so in other words, if I say it just slightly more abstractly, out of this discrete data, I'm building something that's topologically an S1. Just the union of all these zi plus 1s is topologically an S1, and I can talk about its winding number. Okay, so if I specify the winding number equals k, that picks out some interesting part of the subspace in the space of n two-dimensional vectors. It's actually very slightly more interesting because this problem has a cyclic symmetry where you rotate everything by 1, but you have to decide when you wrap around the n, whether you pick up a minus sign or not. So you have to decide whether this means that when n is positive, it breaks up into two cases, or when n is negative. So these are two different cases that you have to pick out. And then depending on what you do with that, the real formula is that the winding number is the floor of k minus 1 over 2. Okay, and the difference between the two cases has to do with whether the end goes one way or the other way. This is a detail at this point. Okay, so that is some part in the space of n two-dimensional vectors. And the claim is that if you then run this whole story, that gives you this geometric object, the amplitahedron, that's labeled by this integer m. In this case, in the simplest case, for m equals 2. But now let me tell you what the story is for m equals 4, which is what we care about for physics. Now I have a bunch of four-dimensional vectors. Now we don't have an obvious notion of winding number associated with four-dimensional vectors. The obvious notion we'd have is to find some S3, something that's topologically in S3, so we can talk about how often it winds around. But there is a very beautiful S3, which is actually naturally in this problem when you have the cyclic structure. What I want to stress here is that all of this structure arises the second I said the word ordering. That's all I put in, is that 1, 2, 3, up to n have a natural ordering. The second the word ordering comes in, everything else that I'm telling you becomes possible. So what is that topological S3? It's the union, so when m equals 2, we had the union, we had formally the sum of all of these simplices, these intervals I plus 1. And of course, if I call this S, of course the boundary of S is 0, and so S is topologically in S1. When m equals 4, the beautiful analog of this is the sum over I and j of these simplices, I plus 1, jj plus 1. Okay, and the set of those tetrahedra glued together to give you something with no boundary. The boundary of S also vanishes. This is topologically in S3, and now I can talk about the winding number of this configuration around the origin. Okay. And the claim is that this problem gives me a winding number that was k minus 1 over 2. This problem gives me a winding number that's actually k minus 3 over 2, floor choose 2. And you can actually do this for general even m, where the winding that we're talking about is labeled by generalization of this, I1, I1 plus 1, I2, I2 plus 1, and so on. And the winding number in general is k minus m plus 1, the 4 of k minus 1, k minus m plus 1 over 2, choose m. Okay. Now, I didn't explain to you where this number comes from, but when if I had 10 more minutes, I would tell you these winding numbers are actually maximal. Okay, so there's something totally canonical about these. They cannot wind around any more than are forced by this. So one way of specifying this subspace in the kinematic space is to find those points in kinematic space that wind around as much as possible. And there's a natural boundary to that region. And now here's the fascinating point. Just that combinatorics of this statement about topology forces that when you go to those boundaries, the space factorizes into the product of lower dimensional spaces of the same type. Okay, so that's the origin of both locality and space-time both space-time locality and unitarity are outputs from this from these simple topological questions. One amusing thing about it is that you can mathematically, you don't have to stop at n equals 4, you can go to n equals 6, n equals 8, any m, and those give you models that have sort of higher versions of factorization. I don't know how to associate them with any standard quantum field theory or Lagrangian, but there's a beautiful structure associated with them where instead of factorizing in 2, you can factorize in 3 or 4 or 5 or different pieces. And finally, there's some completely obvious symmetries associated with this subspace. I don't have time to explain, but the really trivial symmetries in the subspace, these trivial symmetries in the subspace turn into the infinite dimensional Yangian symmetry. So the Yangian symmetry is not only not hidden, you just fall over yourself running into it. Okay, it's just totally trivialized in this space. All right, so that's it. This is one example where we see that some combinatorial and topological questions at infinity, this is now in the kinematic space at infinity, actually determine dynamics. And in the past couple of years, we've been seeing more and more examples of this in more theories, not just for gluons, for scalars, pions, gravity, all kinds of theories, at least in perturbation theory. And regardless of whether these specific ideas will end up being central, what I want you to take away from this is that we have to look for something like this in this space, because in this space there is nothing normal to do. Okay, we have to ask some strange, funny question in this kinematic space has to have enough beef in it to produce answers that have all of the properties that we normally ascribe to things that we associate with path integrals and local evolution in space. Thank you.
All right. Shall I ask a question?
I wonder, in this consideration, do you require well-defined quasi particle so you can consider this?
Absolutely, yeah, and not only that, this is all, I mean, this is all perturbation theory at the moment.
Yeah.
It's just, so we're just talking, yeah.
But for the gluon, sometimes gluon strongly inherent.
Absolutely, absolutely.
But in
yes,
that
yes.
case, whether
Right.
this kind of thing can.
No, so really strict. I mean, really strict. Everything I was telling you about is true at tree level for gluons. Okay. Now, tree level for gluons works at very high energies for high energy scattering process, and then of course something happens at low energies in the confinement and so on. Tree level for gluons in Yang-Mills is the same as tree level for gluons in n equals 4 super Yang-Mills. And there's an all loop order extension of this result, of this kind of picture, for n equals 4 super Yang-Mills in the planar limit. Okay, so there at least the particles make a little more sense. You don't have confinement. It's a conformal theory, so the S matrix is not quite perfectly well defined, but it's close to being perfectly well defined. But the sort of deeper question is definitely there. I mean, that's why there are several sort of, these ideas are on different continents than most of the things that are being talked about that are continuously attached to ordinary local quantum field theory. On the other hand, we're asking questions that are not natural questions for local quantum field theory. You know, scattering amplitudes, despite their historical importance for the development of particle physics, it's not the correlation function of local operators, which is a natural Euclidean question. These are sort of funny, non-local Lorentzian questions that are not well posed in Euclidean quantum field theory. And so the fact that asking them exposes these interesting new, sort of quite different kinds of mathematical structures that we've been used to is the novelty and the interest.
All right, any other questions?
Just to see if I roughly followed what you said. So this maximal winding space,
Yes.
Your physical scattering amplitude has to live in that, or is
No,
it a subset of
no. That's
Okay.
kind of the cool thing. The physical scattering amplitude turns out to be a differential form. Okay, a rational differential form. It's just a function of these z's, and so it has poles. For example, it has poles when the II plus 1, JJ plus 1s become coplanar. That's the only place it has poles, but it's some very interesting numerator. Okay. How can a scattering amplitude be a form? Well, remember I told you they're helicities of the gluons. So the different pieces of the form, dz of this guy, dz of another guy, and so on, actually tell you what the helicities of the particles are that are involved. So all the data sort of matches. So the amplitude is actually a differential form that lives on this kinematic space. And now the interesting thing is that you don't force the data to be winding and so on. But the point is that this differential form is the slave to something. And what it's a slave to is that this differential form has the property, roughly speaking, if you ignore this business that you have to pull it back to a subspace of the correct dimensionality, but roughly speaking, this differential form has a property that it has logarithmic singularities on the boundaries of the space where the winding number just goes wrong. Okay, so there's some interior region where the winding number is right, just like a little more loosely, if I have this picture of a quadrilateral, I have a differential form that lives everywhere. The form lives everywhere, but it's nailed by the requirement that it develops poles of a particular type on all the facets of this geometry. So here, what determines the geometry is not just that I like this polygon or that polytope, but it's just this topological question in kinematic space. You ask for the amplitude to have singularities on the regions where the winding number fails to be maximal, and exactly doing that forces it, and this part is very non-trivial. I mean, it has a sort of two-page proof, but it's kind of slightly miraculous to see how something sort of purely topological like this forces the space to kind of factorize in 2 when you go to one of these boundaries, so that the winding number, it sort of adds. You get some winding number from this side that has to add up to something from the other side to all work, and so on. So factorization is an output from these topological questions.
All right, well, so shall we start at 11?
I have a quick announcement after
Yeah.
you close the session.
Okay, so then let's thank Nima.
I have a quick announcement about the lunch because it may not be clear in the schedule. So